13.2, a lot of the math that we're doing is actually going to look very, very similar to 13.1. So the math itself is really just continuing to work with that simplifying-ish piece. But there's a slight change. Today, in all actuality, we're doing what's known as verifying trig identities. What does it mean to verify something? I mean like the Englishy term, not the mathy term. What does verify mean? You check it. Means the same thing in math. But there are specific things to a verify problem, because that's what the instructions are going to say today. They're going to say verify or verify the trig identity, and it does mean to check. Check if the identity is true. Now, what that means is today you're going to get equations, so there's going to be an equal sign in there this time, and they are trig identities, which means they are equations that are true for all values in which the function is defined. But they're more complicated identities than what are simply on your blue sheets, because in all actuality, there are an infinite number of trig identities out there. But all of those trig identities really can be broken down into about 50 total identities. We don't do all 50 of those identities here, but they all can be broken down and found to have a source in identities that are included on this sheet. Now, we're still not doing with the ones on the back. We will get to those later. So the ones that we're going to be given are all related to things on this front sheet. And we are going to be able to check that they work based on the fact that we know that these work. Verifying a trig identity is a proof, meaning you must show all steps. Now, much like we've discussed in this class, generally speaking, proofs are not like the proofs you did in geometry where it says, given this, prove this. Proofs show up in a lot of different forms. That is one format that you're going to see the proofs. And you could do a 2-column proof with that. These ones, we're not doing a 2-column proof. We are just going to be essentially taking these expressions and we will simplify one or both sides of the equation. Until each side is the exact same. So it doesn't have to get down to its simplest form. It just has to get to be the same thing as what's on the other side. Now note, this says simplify. In all actuality, as we go through and do this, we don't technically have to quote unquote simplify and make things look simpler. We could actually decide, I'm going to make it look more complex. The problem with that idea, though, is that making something look more complex, while really easy to do, there's an infinite number of ways you can do it. And so it tends to cause more issues unless you know exactly where you're going with it. So we tend to simplify. And since we want to simplify, we typically start with the more complicated looking side. Because if you start with the more complicated looking side, generally what you're going to end up doing is you're going to get things closer to looking like the other side first. If you start with the simpler side, you can, don't get me wrong, there's nothing wrong with it. You just might end up making your proof longer. Because there are an infinite number of ways to do all of these problems. There is not one right way with no exceptions. There is never one right way. There are ways that are better than others, but there's never one correct way. There's an infinite number of correct ways. As long as you're following and doing proper math and getting both sides to be the exact same, you're doing the right thing. Now, one of the biggest things that I see that is one of the biggest mistakes that people make when they are verifying is they start doing things to both sides of the equation. And what I mean by that is they're using opposite operations. Which you are not allowed to do. Just like back in algebra, when you learned to plug something back in and simplify it down to see if you got the same thing on both sides of the equation, you weren't allowed to do opposite operations there, because opposite operations is what caused issues in the first place. That's what caused you to get extraneous solutions at times. Opposite operations in trig expressions and verifying these identities can do the same thing. You cannot say, oh, I'm just going to add the 1 to both sides. No. Each side of the equation is its own individual beast that you can only do things on one side. If you're moving something from one side to the other, you're doing it wrong. That's opposite operations. And the last thing that I like to write is just a reminder. When you are simplifying, when in doubt, what's our last resort? That last red flag, that last thing we do if we could find nothing else. Change everything into sine and cosine. So, the process that you follow on this stuff, for the most part, is very much the same as what we'd already been doing. The instructions will say verify instead of simplify. The problems themselves will not just have a single trig expression. They'll have two that are equal to one another. So you'll see things along the lines of cosecant squared theta minus cotangent squared theta equals cotangent theta tangent theta. The first thing you should double check is that all the angles are the same. If they are not, you need to deal with that first, because otherwise the identities don't work. Are all the angles theta? Yes. Sweet, we're good there. Then we pick a side to work on. You want to work with the right side first? The right side is not necessarily the easy or the always the best side to work on in this case. This one we'd have to do it anyway. Generally, you want to start with the more complicated side. On this one, we're going to have to work on both anyway, so we might as well start on the right side. And if you see something like this that you do know exactly what to do with, there's nothing wrong with starting there. Generally, we want to start with the more complicated looking side. I would typically start with this one, but if we want to start here, let's start here. Cotangent times tangent. Multiplied reciprocals, that's equal to 1. Now, since this is a proof, we must have two sides of the equation at all times. The other side, I didn't touch it, so I turn it back into cosecant squared minus cotangent squared. 1 does not simplify any further, which means I have to work on the left side of the equation now. I looked through those red flags because I'm just simplifying each side individually. My angles are the same. I don't have multiplied reciprocals. Squared trig, adding and subtracting other squareds. Other squareds or 1s. In this case, it's other squareds. Are cosecant squared and cotangent squared in the same trig identity? Yes, they're the third Pythagorean identity. So, it's not matching the identity perfectly, so I tend to write it off to the side and say, can I manipulate this equation, this identity, to look like cosecant squared minus cotangent squared? I could subtract cotangent squared from both sides. Cotangent squared minus cotangent squared cancels. I'm left with 1 equals cosecant squared minus cotangent squared, which is what I wanted it to look like. Therefore, cosecant squared minus cotangent squared becomes 1. 1 equals 1. As soon as both sides of the equation are the exact same, I stop. I proved it. I verified it. I showed that both of these are the same because they both simplify down to a 1. Sine squared over 1 minus cosine equals 1 plus cosine. Are the angles the same? Do you have multiplied reciprocals? Squared trig pluses or minuses with 1? No, I've got regular trig pluses or minuses with 1, but those are not Pythagorean identities. Adding or subtracting fractions? No, I just got a single fraction equal to something that's not a fraction. Factoring. Algebra. When in doubt. Everything is already sine of theta and cosine of theta. Okay. Now, the one thing that's going to shift a little bit when you are verifying is sometimes they're going to have things on there that maybe don't perfectly fit our red flags. And so you have to look at what you have on the problem and say, okay, what do I recognize? Here's what I recognize here. I recognize I have both a 1 plus cosine and a 1 minus cosine. Those are conjugates of one another. When I see conjugates of one another, I think, is there a difference of squares somewhere? Now, there's not currently a difference of squares somewhere. But, could I make something have a difference of squares somewhere? There's a couple different ways to do this. One way is just straight up brute force. Get the thing to look like what you want it to look like. Say, and this especially works nicely when you have a fraction on one side and a non-fraction on the other. Because that non-fraction side, I can make it a fraction. I could say, this in all technicality is over 1. Now that's not its own separate step to do that, but if it helps you see it, I will write it as a separate step. Why did I write that? Don't mind me. I'm getting ahead of myself. Currently, I have 1 plus cosine of theta, and all that I could do to change it into a fraction is put it over the top of 1. Don't mind me. Like I said, I got ahead of myself. Okay, so sweet. Now I've got fractions on both sides. It's closer. Now, I want those fractions to be the same fraction. Easiest way to get the same fraction on both sides, or one way to manipulate to get the same fraction on both sides, is just say, hey, what would be the common denominator between those two? 1 minus cosine. Get them both to have the common denominator. In fractions, you can do that. This one would have a common denominator if you multiply both the top and the bottom by 1 minus cosine. Remembering that when you do that, there is technically parentheses around anything with a plus or a minus in these fractions. So I'm going to have to do some distribution. The left side I didn't touch, so I put it back, because throughout the entire proof, I do need both sides of the equation. Okay, numerator I'm going to FOIL out. 1 times 1. 1. 1 times negative cosine. Negative cosine. Cosine times 1. Positive cosine. Cosine times negative cosine. Negative cosine squared. Over the denominator of 1 minus cosine of theta. Now this doesn't look, maybe not look like I got closer to having the both things be the same on each side, but they have the same denominator, so I am getting closer. Now I noticed that on the right side I can simplify some things. What's negative cosine plus cosine? 0. So I'm left with 1 minus cosine squared theta over 1 minus cosine of theta. Red flag just popped up in the numerator here. Squareds plus or minus 1s. Pythagorean identity. The Pythagorean identity that has cosine is cosine squared plus sine squared is equal to 1. Can I rewrite this identity to get a 1 minus cosine squared? If I take the identity and subtract cosine squared from both sides, I'm left with sine squared is equal to 1 minus cosine squared. Is sine squared what I wanted that to turn into? Yes. Sine squared theta over 1 minus cosine theta equals sine squared theta over 1 minus cosine theta. I'm done. How do I know that I'm done with this problem? Both sides are the exact same, and I'm going to emphasize exact. If I had these flipped around and said negative cosine plus 1, not the exact same. We know it's equivalent, but they have to be the exact same. For today, I'm only going to give one more example for you. Because in all actuality, the math behind this is the same, except the nice thing about this is you know where you're going with it. You know what you're supposed to get on both sides. Yeah, maybe not exactly, because you don't know necessarily exactly where you're going to end the problem, but you do have the extra help of the fact that you know both sides are going to turn into the same thing. first thing we should be checking? The angles are the same, are they? No, so we got to deal with that first. Cotangent of a negative theta is negative cotangent theta, but here's the thing. That squared can mess with things a little bit. In all actuality, when you have this cotangent squared of negative theta, what you actually have is cotangent of negative theta being squared. Notationally, that's what that means. Cotangent squared of negative theta means cotangent of negative theta, all in parentheses, getting squared. Which means when I pull that negative out, it's technically this. So, negative cotangent of theta, which I don't technically need the parenthesis around that theta at this point, squared minus cosine squared. I don't necessarily need the parentheses there either. I don't know why I put the extra parenthesis. Equals sine squared theta. Now, in all actuality, you are allowed to edit things on both sides of the equation at the same time, as long as you're not doing opposite operations. You're not moving something from one side to the other. So on this side, I can deal with that negative theta in the same step. This should be screaming that you should do some algebra right now. Generally speaking, parentheses, you don't want to keep them. Which parentheses do I deal with first on the left side? Big parenthesis or little parenthesis? PEMDAS, what do you deal with? The biggest parenthesis or the smallest one inside of it? The smallest one inside of it. Negative cotangent getting squared. A negative squared is positive. Tangent squared theta. This is a positive cotangent squared theta. Same thing on the other side. That's a positive cotangent squared theta. I still have parentheses. How do I deal with the parentheses on this side now? Distribute. Okay, I end up getting tangent squared theta, which is multiplied by cotangent squared theta, minus tangent squared theta, which is multiplied by cosine squared theta. The right side, just leave it alone. My parentheses are gone. I'm no longer focusing on algebra. I'm going through all my other red flags. My angles I already dealt with. You should only have to deal with those once at the very beginning, and then you should be good. Next thing I tell you to look for. Most of the red flags don't go in order. The first two and the last one do. Check the angles. Check for multiplied reciprocals. Do we have any? Yeah. Tangent squared times cotangent squared. 1. Tangent times cotangent is 1. Tangent squared is tangent times tangent. Cotangent squared is cotangent times cotangent. So I just end up with tangent and cotangent multiplied twice. So 1 times 1 is just 1. Don't have any more multiplied reciprocals. I do see squared trigs and ones, but if these two squared trigs are multiplied together, can I touch them with that 1 and work with Pythagoreans? No. So, I move on. Factoring? No. Algebra? No. Added fractions? No. Algebra, I already checked multiplied reciprocals. When in doubt, change everything into sines and cosines. Tangent squared as sines and cosines. I'm pretty sure there's more than just one person who's able to talk in this class, just saying. It's sine squared over cosine squared. Times cosine squared theta. I will tell you this right now. Generally, if I change one side into all sines and cosines, I'm going to have to change the other one later anyway. So I'll probably change it at the same time too. I don't have to, but I can. Cotangent squared. Cosine squared over sine squared. See anything? You can cancel some things. This is technically cosine over 1. When I multiply these, the cosine squareds are going to cancel. This is technically sine squared over 1. When I multiply these, the sine squareds are going to cancel. 1 minus sine squared theta is equal to cosine squared theta. It's a modified Pythagorean identity. It's one we've done a lot. We very commonly show up with 1 minus sine squared or 1 minus cosine squared because this identity is really easy to modify into that, and it's very common that they modify it into that. So that side is indeed cosine squared theta. Cosine squared equals cosine squared. I'm done, and I know I'm done because I've got the exact same thing on both sides. Okay. Today's homework assignment is a little bit different than many homework assignments. I've got some different rules on it, and I have some different rules on it for a reason. Because verifying trig is going to be one of the things that not only helps us with simplifying trig, so it practices essentially 2 of the main keys of the chapter, and also because in order to solve problems where you're verifying and simplifying trig, really it comes down to getting the practice of recognizing the patterns. So, a couple things about today's assignment. First off, today's assignment actually is today's assignment, Monday's assignment, and Tuesday's assignment all put into one assignment. Because everyone goes at a different pace, I put it all on one just to give you the chance to kind of go through at your pace as necessary, get done with it what you can, when you can, as what is necessary for you. So it is a longer assignment because it's technically 3 days all put together. It's also worth more points. Here's questions 8 through 48. It is worth 10 points. I want you going through and getting the practice at this because very, very few people can do simplifying and verifying trig without getting that practice, a good chunk of practice. It is due on Wednesday. It's not the typical 2 days. It's got 1 extra day in there because it's a multi-day assignment. I also need you to be timely with this one. It's the only assignment that if you are turning it in late, I am taking points away. Need you to stay on top of it. You got about 20 minutes today.